So hello, today we discuss dimension of an infinite dimensional Banach space. Dimension of an infinite dimensional Banach space. So this is our topic. I think we have done this earlier. So, but actually it's a unit segment. It was not a unit 1. Okay. So let us state this theorem here. Banach space cannot have denumerable bases. Denumerable means countably infinite. Okay, denumerable bases. So proof. For the proof, we first prove the following lemma. Okay, we first prove the following lemma. And what's the lemma? Interior. Okay, it is interior of any proper subspace. Interior of any proper subspace of a normed linear space is empty. So now the proof of the lemma. So let's take any proper subspace. Let X be a normed linear space, be a normed linear space, and Y be a proper subspace of X. Proper subspace of X. That means Y is not equal to X. Okay, we show that this interior of Y is the empty set. So assume on the contrary that this Y has interior point. Assume on contrary that there exists some point Y which is in the interior of capital Y. Okay, so this Y is interior point of Y. Then we can find a ball with center at Y contained in capital Y. Then we can find some ball that means there exists R positive such that the ball with radius R, open ball, okay, centered Y is contained in capital Y. Okay, so now we prove that any point of X is in Y. That actually we show that this Y is equal to X, which gives us a contradiction, as Y is a proper subspace of X. So let's take any point of X. Let X belongs to X. Okay, X belongs to X. Then this x by norm x. Okay, so I want to scale this x so that it will lie in this ball, right? So how do I do that? Then so I want to find I want to prove that this x minus y is less than r. So this x with some scaling factor, okay, x with some scaling factor alpha times x. So can I do that? This is x minus y, okay, then I write plus y. This will go, okay. So I have to scale and let's see this point, okay, this one, x divided by norm x, and then should write here r by 2. Okay, this point right, what's the norm of this one? This is r by 2, which is less. Okay, it's less than r, right? So let's write this plus y here again. Let's see this point. This is the point, okay. Then this point belongs to the ball b r y. ना ये जो पॉइंट होगा ना ये इस बॉल में होगा. Why? As the distance of this point from y, you can see it's less than r. As distance of this point x by norm x r by 2 plus y, this is the point. It is distance from y, that means minus y here, this distance. What's this? Y and y will go, so this will be r by 2, okay, which is less than r, straight. So that means this point lies in the ball, and but this ball is contained in y, so that means this point also lies in y. This gives x divided by norm x, then r by 2 plus y, it also in y. Y is already in y क्योंकि y का point है, y is the interior point of y, ना? It's in y, so it means that now y is a linear space, it's a subspace, so x by norm x, then r by 2 plus y minus y, this is also in y, as y is a subspace, y is a subspace. These two will go. This implies x divided by norm x and r by 2, it is in y. Now again this y is a subspace, so any scalar multiple of this point, ये जो point यहाँ पर y में आ गई, it is any scalar multiple of this point is also in y. So let's take this scalar multiple. Let's write this 2 by r and norm x. So this is your scalar. Then this point, this is also in y, as y is a subspace. Okay, so but this gives norm x, and norm x will go, r by 2 by r and r by 2, they will go, it's just x belongs to y, which means that every point of x is in y, that means x is equal to y. So it's a contradiction. How is a contradiction? So a contradiction. So therefore interior of y is the empty set. Now we come to the proof of the theorem. Proof of the theorem. So we have to show that Banach space cannot have denumerable basis. Assume again on contrary that this y has denumerable basis. So assume that not yx, assume that so let's start this let x be a Banach space and assume that this has a denumerable basis. Let x be a Banach space and assume that x has a denumerable basis. हमें प्रूव करना कि it cannot have denumerable. Suppose we assume on contrary that it has a denumerable basis. It has a denumerable basis, and let's assume that this is be the basis, that this is the basis e1, e2, so on and so forth. It's countably infinite set. B its basis. Now let's define these spaces. Define yn, which is the spawn of first n vectors, these basis vectors. Okay, so it's a finite dimensional subspace, okay, of x. Then each yn is a finite dimensional subspace of x. y1 is generated by 1, y2 is generated by 2 vectors, okay, is a finite dimensional subspace of x. But x is given a Banach space, and we also know that any finite dimensional normal linear space is a Banach space, and therefore yn is a Banach space, and therefore yn is a Banach space. Okay, because we know that any finite dimensional normal linear space is a Banach space, so that means each yn is a Banach space. Now since x is Banach space, x is a Banach space, अब क्योंकि x भी Banach space है और yn इसका subspace है और ये भी Banach space है, so therefore yn is closed, therefore each yn is closed. आपने वो एक रिजल्ट किया है, अगर आप याद होगा वो, अगर x Banach space है फर्स्ट यूनिट में आपने किया है और y इसका सबस्पेस है, देन y इज Banach if and only if y is closed. या मीट्रिक स्पेस में आपने किया होगा, given a complete metric space x and y is a subspace of x, then y is also complete if and only if y is closed. So here yn is a Banach space, so that it must be a closed, because as this x it's a Banach space है, क्योंकि ये subspace है किसका, Banach space का, तो अगर ये खुद Banach होगा then it must be closed. So again we have this x is obviously union of y's. X is union of y. आप x में से कोई भी पॉइंट लीजिए, वो किसी न किसी y का पॉइंट होगा. देखिए अगर आप x में लोगे, x की बेसिस है ना, ये x की बेसिस है, so you can find some finite vectors from this basis set such that x is the linear combination. X is alpha 1 e1 plus alpha 2 e2 plus alpha n en for some n. But this vector, it belongs to yn, as this yn is a subspace of x which is generated by e1 e2 en. So that means any x in y is in some yn for some n. So that means this x is union of these two spaces. Now again this we can apply Beer category theorem, which states that any complete metric space cannot be written as a countable union of no dense sets, and here x is complete, so that it cannot be written as countable union of no dense sets, but here it's a countable union of these sets yn, so that means these yn they cannot be no dense. But we know that any Banach space cannot be written as a countable union of novaidence sets. Countable union of novaidence dense sets. It's by Beer category theorem. Okay, Beer category theorem. So here it's countable union. So that means each y is not novaidence. So this means so therefore there exists some n naught such that y n naught is not novaidence. ये novaidence नहीं होगा this. So which precisely means that interior of yn naught closure is the empty set. This is the definition of novaidence set. But yn naught, they are closure sets that you have already seen, because they are the Banach spaces of they are subspaces of a Banach space, and they are also Banach space. So that means they are closed actually. That we have already proved. Each yn is closed. So which means that interior of y, this is non-empty. Okay, novaidence is not novaidence. Okay, y naught is not novaidence. Not novaidence. Novaidence का मतलब ये है कि interior of the closure is the empty set, but it's not novaidence. So that means interior of the closure set is not empty. And again this y naught, this is a closure set. So that means y naught closure is y naught. So this is empty, non-empty. Okay. So which means that interior of y naught is non-empty. But this y naught, it's a proper subspace, but y naught is a proper because y naught is a finite dimensional space, right? It is generated by n vectors, and x is not finite, it's an infinite dimensional space. So y naught is a proper subspace of x, which is a contradiction, because we know that any proper interior of any proper subspace is empty, but here interior of y naught is non-empty. A contradiction, a contradiction. So therefore x cannot have denumerable basis. So any Banach space cannot have denumerable basis. Any Banach space. अब इसकी एप्लीकेशन पार्ट क्या होगा? इसका एप्लीकेशन पार्ट, you know that this set of all polynomials जो है, it's a normal, it's a linear space, और इसकी जो basis है that's 1x square. So we know that set of all polynomials P AB, which is this set, okay, a n x power n plus a n minus 1 x power n minus 1 plus a1 x plus a naught, where these ai's, they are the scalar field k, and x belongs to the interval AB. This is a linear space. This is a linear space. You can add the polynomials, and a scalar multiple of polynomial is again a polynomial. So this is a linear space, and what's the basis set of this? This 1x square, so on and so forth, is the basis of, ये इस सेट की basis है. So this is obviously countable infinite, है ना, this set. So by above theorem we cannot define any norm on P of AB which makes it Banach space. So there are norms on P of AB. In fact, we have norms, and we have an infinite number of norms on this P of AB. P of AB is a normal linear space. We can define any number of norms, in fact. So given any polynomial, we can always define norm on that polynomial. That's very simple. But any norm on P of AB cannot make P of AB a Banach space. Why? Because it has a denumerable basis. So therefore P of AB has a denumerable basis. Therefore P of AB has a denumerable basis. And hence cannot be a Banach space. It cannot be a Banach space. Banach space with respect to any norm. With respect to any norm. It's not a Banach space, okay? This space. आपको ये बात समझ आ गई? P of AB is not a Banach space with respect to any norm. हाँ, अगर आप n को फिक्स करोगे ना, मतलब आप लोग ये सेट ऑफ ऑल पॉलिनोमियल्स ऑफ डिग्री लेस आर इक्वल टू n, उस केस में ये Banach स्पेस है, क्योंकि उस केस में इसका जो बेसिस सेट है वो होगा 1x x स्क्वायर x पावर n तक होगा. उस केस में n प्लस 1 डायमेंशनल स्पेस होगा. तो इन दैट केस इट विल बी अ Banach स्पेस विद रिस्पेक्ट टू एनी नॉर्म. बट इफ यू टेक ऑल पॉलिनोमियल्स, आप डिग्री पर बाउंड डिग्री को रेस्ट्रिक्ट नहीं करोगे लेस आर इक्वल टू n. यू टेक एनी पॉलिनोमियल ऑफ डिग्री 3 4 5 6 so on and so forth, any degree. If you take set of all such polynomials, then that set it also follows a linear space, but that linear space, it's a normal linear space. We can define norm on that space, but that linear space cannot be Banach space with respect to linear. देखिए अब डिफरेंस कहाँ पर है. आप अगर डिग्री को रेस्ट्रिक्ट करोगे लेस आर इक्वल टू n लोगे, then it will be a Banach space with respect to any norm. But if you take all polynomials, then it will not be a Banach space with respect to any norm. Okay, next we know that if x is a finite dimensional normal linear space, finite dimensional normal linear space of dimension n, then x star is also finite dimensional. This is also finite dimensional of same dimension, So that's in this case, finite case, we have dimension of x is same as dimension of x star and both are equal to n. तो अगर x फाइनाइट डायमेंशन होगा, उस केस में इसका जो डायमेंशन होगा दैट कैन नॉट इंक्रीज. क्या ये ट्रू है इन्फिनाइट के केस में? इज इट ट्रू फॉर इन्फिनाइट केस? इज इट ट्रू फॉर इन्फिनाइट केस? क्या इन्फिनाइट केस में भी क्या डायमेंशन इंक्रीज नहीं होगा? सपोज इसका डायमेंशन, सपोज इसकी बेसिस जो होगी वो सपोज डिन्यूमरेबल सेट होगा, कोई ना काउंटेबल बेसिस इसकी होगी. क्या एक्स स्टार की भी काउंटेबल बेसिस होगी? यस. आपने वो डबल बेसिस तो डिफाइन की होगी ना. अगर x कोई स्पेस है फाइनाइट डायमेंशन, इसकी बेसिस अगर e1 e2 en है, तो आप x स्टार के बेसिस आप कंसिडर कर सकते हो e1 स्टार e2 स्टार en स्टार. तो बोथ हैव सेम डायमेंशन n. But what happen if x is taken to be an infinite dimensional space? In particular, infinite के केस में आपके पास choices है. One choice is the countable, countable infinite, and second choice is uncountable. तो first, if x has a countable basis, क्या x star की भी countable basis होगी? Yes. Any idea? So as you know that this as dimension of P of PB, set of all polynomials. It's an infinite dimensional space. Its dimension is L of naught. You know, 1 x square, x cube, so on and so forth. Now, what about this dimension? Dimension of its dual space, P star AB. Is it equal to n naught? क्या ये n naught के बराबर है? देखिए आपने एक रिजल्ट किया है. गिवन एनी नॉर्मल लीनियर स्पेस x, दिस x स्टार इज ऑलवेज ए बनाक स्पेस. किया है आपने. The dual space is always Banach space. Okay, so this P star, it's a Banach space. It's a Banach space. So it cannot have a denumerable basis. So that means dimension of P star AB cannot be n L of naught. It cannot be L of naught. It's greater than L of naught. It is. तो इन्फिनिट के केस में जो डायमेंशन है ना, ये प्रिजर्व नहीं रहता है x, और इसका ड्यूल का जो डायमेंशन दे आर नॉट सेम. ओके, सो इट्स ग्रेटर देन L of naught. ओके, it's greater than L of naught. So whenever x is an infinite dimensional space, the dimension of x star is at least c, the continuum hypothesis. So you can say this dimension of P star. So next coordinate क्या है? That is c. ना, next coordinate L of naught के बाद जो coordinate वो c है, the continuum hypothesis. So it's greater or equal to c. It's greater or equal to c. C is the cardinality of the set of real numbers. Okay, uncountable. So that means we can say that if x is an infinite dimensional normal linear space, infinite dimensional normal linear space, then dimension of x star is always greater or equal to c. It cannot be L of naught. It's always greater or equal to c. So this was about dimension of infinite dimensional Banach space. Now our next topic is it's the separable spaces. Okay, separable normal linear space or Banach space. Okay, what's separable space? Definition of separable space. Do you know? Do you have any idea about separable spaces? आप definition ही बता दीजिए मुझे. Definition of separable space. ये हमारा जो नेक्स्ट टॉपिक है, दैट्स दिस वन इज द लास्ट टॉपिक, सेपरेबल स्पीसीज. इसमें हमें कुछ क्लासिकल स्पीसीज की सेपरेबिलिटी चेक करनी है. सो यू शुड नो एटलीस्ट द डेफिनेशन ऑफ सेपरेबल स्पीसीज. यस,
which is a Hausdorff space.
Hausdorff space.
Hausdorff property. This satisfies the Hausdorff property.
Okay. So let's first define this separable space. Okay, definition. a Banach space X is said to be a separable space, or a separable Banach space, or you can simply say separable space if it has a countable dense subset. So that's the definition. That means there exists a subset y of x such that y is countable. एक तो y countable होगा, and second it is dense in x, and dense in x means that its closure is equal to x. इसका जो क्लोजर होगा वो किसके बराबर होगा? वो x के बराबर होगा. ये डेफिनेशन क्लियर हो गई. इसका क्लोजर का मतलब क्या है? द स्मॉलेस्ट क्लोजर सेट कंटेनिंग y. y क्लोजर मीन्स द स्मॉलेस्ट क्लोजर सेट कंटेनिंग y. तो कुछ एग्जांपल्स हम सिंपल एग्जांपल में पहले लूंगा. स्टार्ट विद अ सिंपल एग्जांपल हियर. This R, the real line, is a separable Banach space. Is a separable Banach space. It's a separable Banach space. Y as Q जो है Q closure is R, and this Q is countable. Q काउंटेबल सबसेट है, और Q इज अ सेट ऑफ रैशनल, और इसका क्लोजर जो है ना वो R के बराबर है. सो दैट्स व्हाई दिस R is separable. नेक्स्ट एग्जांपल C complex spleen is a separable Banach space. So this set, if I define y, this set A plus iota B, where A and B they are rational numbers, then this y is countable because Q is countable, then y is countable, and y closure is equal to. So with respect to any norm you can see y closure is equal to C. Y closure C के बराबर है. So these are the simple examples of separable spaces. Next example is the set of all polynomials is a separable space. Show that this P of AB with respect to the given norm, कोई norm इसको define करेगी, is a separable space. It's not a Banach space, but it's a separable normal linear space where what's the norm? Where this norm of any polynomial a n x power n plus a n minus 1 x power n minus 1 plus say a1x plus, you can define a sup norm, or just you can add these scalars here with mod. That's also a norm. So let's see this. It's mod of a n plus mod of a n minus 1 plus mod of a1 plus mod of a with respect to this norm. So this is a separable normal linear space. Or you can define or norm of I think this is let's take this norm here. Plus A naught. You can take just the supremum of these spaces, or you can take this maximum of mod of an minus 1 mod of a1 mod of a naught, इनका जो मैक्सिमम होगा, मैक्सिमम ऑफ दिस. You can define one more norm on that. That's the, जैसे ये कि this is actually continuous function. Every polynomial is a continuous function, so this polynomial is also a continuous function on the closed interval AB, so therefore it's a bounded function actually. This is bounded function, so we can define sup norm also. It's a bounded continuous function. It's a subset of CAB. So one more norm you can define here, or you can define this norm an x power n plus a1x plus a naught. Let's define this. It is the supremum of what, the value, okay, supremum of this a n x power n plus a1 x plus a naught, where this supremum runs over x. Okay, this it is a less or equal to x less or equal to b. Okay, with respect to these norms, it's separable space. This P of AB, it's a separable space. अब अगर ये सेपरेबल है तो सबसे पहले आपको एक काउंटेबल सबसेट चाहिए इसका P of AB का, which is also dense in P of AB. So what's that countable dense subset? Solution. Let's define this set. Let's define y. So let's take here this not take the scalars, all scalars. I will take this the coefficients. Just the coefficients, they are all real numbers. Okay, or real polynomial space. We will discuss. Complex I can do the value. Okay, I will discuss here linear space. This real linear space. Okay, the coefficients are real numbers. So let's then define this an x power n plus an minus 1 x power n minus 1 plus a1 x plus a naught, such that these coefficients ai, they are all rational numbers here, where I varies from 0 to n. Okay, so this is the set of polynomials with rational coefficients, So then this y is countable, because we know that the countable union of countable sets is again countable. So this y is countable, it's a countable subset of P of AB. Now you can see this, we show that this is dense. We show that y closure is equal to P of AB. This is P of AB, this y closure. So this is not too difficult. You can apply this denseness of Q in R. Q is dense in R, that you can apply here as this is with rational coefficients. So we can always approximate any polynomial with real coefficient with this polynomial with rational coefficients. That can be always done. So if I choose any epsilon positive and any polynomial with real coefficients, so let epsilon be any positive number. So what do we mean by dense actually? Dense का मतलब क्या है? सबसे पहले मैं इसको explain करूँगा denseness का मतलब क्या है. So, ये actually फर्स्ट सेमेस्टर का कोर्स है आपका dense space. So dense का मतलब क्या? dense का मतलब ये है कि मतलब अगर आपके पास नॉर्मल लीनियर स्पेस में हम डेंस को डिफाइन करेंगे. अगर ए सबसेट है किसी नॉर्मल लीनियर स्पेस एक्स का, तो हम कैसे कब कहेंगे ए डेंस होगा एक्स में? ए तभी डेंस होगा एक्स में इफ फॉर ईच एक्स इन एक्स एंड एप्सिलॉन पॉजिटिव. कोई भी एक्स आप एक्स में लो और एप्सिलॉन कोई पॉजिटिव लो, then there should exist some point a in a such that norm of x minus a is less than x. That means you can approximate every point of x by some point of e. Okay, so that's dense. A is dense in x. You can approximate points of x by points of e. For each x in x, for each epsilon positive, there should exist a in a such that norm of x minus a is less than epsilon. That's the definition of the denseness. So now here we have to show that y is dense in p of p. So let's take any polynomial. Let's take any polynomial, say p. Let p be equal to, say, p of x is equal to a n x power n plus a1 x plus a naught. Suppose it belongs to p of ab, and let's take any epsilon positive. Okay, then this a and they are real numbers, so we can approximate them by rationals. Okay, then we can choose actually we have to prove that there should exist some qx. Okay, हमारे पास कोई qx मिलना चाहिए with rational coefficients b, with rational coefficients say b n x power n plus b1 x plus b naught. We have to find this qx with bn belongs to q such that norm of px minus qx is less than epsilon. This ये हमें मिलना चाहिए. So how do we define that this qx? Let's epsilon by n is a positive number, so so I can find since epsilon by n is positive number, it's a positive number, and q closure is r, so given any real number I can find some rational number. So there exists say bi, a rational number where 1 equal to this I is equal to 0 1 2 up to n, such that mod of this ai minus bi is less than epsilon by n. This ai, it's a real number, so each real number can be approximated by rational number because rationals are dense in real. So here epsilon is epsilon by n. Okay, so given any polynomial I can fix this n then. Okay, आप polynomial है ये degree 3, then in that case n is 3. So जब भी आप polynomial को fix करोगे, once you fix a polynomial, so you can find this fixed natural number n. So this is now fixed, okay, for this polynomial. So this mod of ai minus bi, it's less than epsilon by n. Now let's find this norm of px minus qx. What's this qx? Where so let's define first qx, then we calculate this. Okay, so let's define this qx. Let's define qx. Let q of x be this polynomial bn x power n plus b1 x plus b naught. So then this qx, it's in q, it's in y, because y is a polynomial with rational coefficients, and this q is a polynomial with rational coefficients because bi's are rational numbers. We can find bi in q. Here you should write q. Okay, they are rational numbers. This is in y, and let's calculate now this norm. This is the simply the difference of these two polynomials. So it's let's apply the first norm that you had defined here, the sum of the modulus of the scalars. So this is a mod of an minus bn plus mod of an minus 1 minus bn minus 1 plus mod of a1 minus b1 plus mod of a naught minus b naught. Okay, see this. Now each ai minus bi is less than epsilon, so each are less than epsilon by n. So in fact you should choose here n plus 1. Okay, so instead of n you should choose epsilon by n plus 1, epsilon by n plus 1. So each is less than epsilon by n plus 1, so it's less than epsilon by n plus 1 plus epsilon by n plus 1 plus epsilon, and they are total in n plus 1 term, so it's equal to n plus 1 times epsilon by n plus 1, which is equal to epsilon. So thus norm of px minus qx is less than epsilon. So that means for any polynomial px in p of ab and any epsilon positive, we can find a polynomial q in y such that norm of px minus qx is less than epsilon. So therefore y closure is equal to p of ab, and hence p of ab is a separable normal linear space, and hence p of ab is a separable नॉर्मल लीनियर स्पेस. और दो नॉर्म्स मैंने डिफाइन किया वो आप खुद करोगे, उसकी वहाँ पर भी आपको हर किसी एप्सिलॉन पॉजिटिव के लिए आपको कोई ना कोई पॉलिनोमियल मिलनी चाहिए. तो आइडिया मैंने दिया है कि कैसे आपको कंस्ट्रक्ट करनी है ये पॉलिनोमियल. यूज़ करना है क्यू इज डेंस इन आर, वो उसका आपको यूज़ करना है सेट ऑफ रैशनल्स इज डेंस इन सेट ऑफ रियल नंबर्स. सो यू कैन अप्लाई दैट रिजल्ट एंड यू विल सी दैट पी ऑफ ए बी is separable with respect to any three norms जो हमने ऊपर डिफाइन किए हैं. So this is the end of the lecture. Now if you have any question you can ask. Yes.